Okay, thank you very much. So my name is Alp Bassa. I'm a research scientist at Veridice. Let me very shortly talk about Veridice. So we are a blockchain security company, especially focusing on ZK-based security. Most of our team members come from academic backgrounds, so we use like cutting-edge new research results, both in all our work and in all our tooling. And we do audits, and while doing audits, we sometimes do need some tools by ourselves, and we try to make those tools also available for others to really check the security of their own circuits and their own systems. So I'll talk today a bit about the theoretical background, but if you want to see things in action, then tomorrow at 7, there will be a workshop run by Andrea. So there you can really see the outcome of all the math that you will see today. And Andrea will also have a talk tomorrow at 6, if you want to listen to that. Okay, so my aim today is to talk a bit about how SMT solvers can be used in the automated detecting of bugs in ZK circuits. And so at the end of the day, I'll talk quite a bit about math, but at the end of the day, if I'm kind of able to convey to you our enthusiasm about SMT solvers, that would be, then I would have reached our goal. Yeah, so today I'll be talking about under-constrained circuits, but of course the same ideas you can also use for the detection of other sorts of bugs in circuits. Yeah? Okay, so as you know, let me maybe skip these. As you know, in many of those, if you have a ZK proof, for instance, there are always two parts involved, right? There's one computation part, which is also called witness generation. Given an input X, it gives you an output Y. And then there's the other side to it, which is about the constraints. So basically, you want to have a set of constraints, which will in most cases be polynomial equations. And you want that these constraints should as closely as possible reflect the computation. Yeah, so what you want to do is, if there is a valid computation, it should pass all the constraints, and nothing else should pass, basically. Yeah? And you have an under-constrained circuit if the following happens. So if there exists an X and Y, so if you have an input-output pair such that f of X is different from Y, so on input X, you don't get output Y in the computation. Yeah? So you should think of F as the computation. So the output is not Y, but the tuple X, Y satisfies all the constraints. Yeah? This you don't want to happen, because that will indicate that most likely there is a bug somewhere and you should be careful. Yeah? And the idea today is how to really detect this, yeah, automatically. So basically, what we really care about is this equivalence. So ideally, the computation and the constraints, the equations, should be equivalent. So if you want, you can rephrase it as f of x should be equal to y if and only if the input-output pair xy should satisfy all the constraints. But in most cases, this is not the case, and that's when we run into problems. Yeah? Okay, so there are various strategies to detect under-constrained circuits. So static analysis is one of them. So you just apply some predefined rules to quickly detect if the circuit is properly constrained. So at Veridice, we use a whole hierarchy of tools, from very simple ones to very sophisticated ones, including fuzzing, static analysis, formal verification, and so on. So static analysis is somewhere in the middle, but today I want to talk about SMT reasoning, where you really can prove things about. So you get some soundness really out of it. So the idea is that that under-constraintness can be expressed as a formula in first-order logic. Yeah, so what we want is we want to forget about the function f for now. We just care about the circuits. So we have only access to p. So let's express under-constraintness just using p. And the way to do that would be to say, I want the following not to happen. I don't want that there is an input x, output y1, and output y2, such that both xy1 and xy2 satisfy all the circuits, and y1 is different from y2. Yeah, because in general, if you have a given input x, you should have a deterministic output y. If you have two different outputs, then there is probably a problem there. And if you want to check whether a given circuit is satisfiable, this should remind you of the classical satisfiability, Boolean satisfiability problem that you know in computer science. So basically, in that case, you have a logical formula, and you're asked to see if there is a satisfying interpretation for it. So you have some logical variables and ands and ors and nuts, and you want to see whether there's an assignment of truth values to those variables that makes the statement true, which is a difficult question in general, so it's known to be NP-complete, right? But in our case, on top of this difficulty, we have an additional difficulty, namely, we are not working just with logical symbols and truth variables, true or false. We're working with other objects. Our circuits are polynomial equations defined over finite fields. So we have finite field elements, we have to add them, we have to multiply them, and so on. Yeah? And that's when SMT reasoning comes into the game. So SMT stands for satisfiability modulo theories. What you basically do is you take a SAT itself, just the Boolean satisfiability, and you add on it additional structure. So you generalize SAT to more complex formulas, so you add some additional theory. This could be, for instance, the theory of integers, the theory of real numbers, or finite fields. In our case, it would be the theory of finite fields in most cases, but you have a whole list of other theories that you could consider. And two of the most famous SMT solvers are Z3 and CVC5. So what SMT solvers do is they just take a first-order logic formula and a background theory, so for instance, the theory of finite fields in our case, and they say they either output that this logical formula is not satisfiable, or they say it's satisfiable and provide you with a satisfying model for it, right? And just to give you an idea what models are, I mean, you could, for instance, the simplest model would be you can look at the theory of integers just with addition. You do not include multiplication. So this is just a linear integer arithmetic, and this is complete and decidable, and but it's not very expressible. Yeah? So you can't talk about divisibility, you can't talk about prime numbers, no nonlinear equations, and so on. You could add multiplication to this theory. You could look at the theory of integers with addition and multiplication, but then you get something incomplete and undecidable. Yeah? So it is not true in this case that if you have a given statement that you can deduce either it's true or you can deduce that its negation is true, and you also have no algorithm to decide whether a statement is true or not. Yeah? So famous Gödel incompleteness theorems, etc. Just to give you a bit more of a visual example, you can think of the theory of the real numbers. If you, again, just include linear real arithmetic, you would be in the world of simplex method on all of those things. Or you can look at nonlinear linear arithmetic, which surprisingly, so that's a result by Tarski, is complete and decidable, right? So you can approach it algorithmically. You have quantifier elimination, that's a very strong tool. And they're very fast algorithms like cylindrical algebraic decomposition and so on. Yeah, so just to give you an idea of possible theories that are around, these are, for instance, the list of theories that you can use inside the CVC5 solver. I want to just give you very quick examples of some applications of SMT-based reasoning or some quantifier elimination. So you could have, for instance, those three constraints over there over the real numbers, and your solver will have a certain syntax. You enter the constraints in that syntax. So you would basically be saying, I want to be inside the red circle on the blue curves, and the x, y coordinate should be distinct. And then the solver will pop out the result -2, -1/2, right? And you have quantifier elimination, so what you can do is even you can give some formulas that have quantifiers in them. Yeah? So this is something really spectacular if you think about it. You can give a formula like there exists an x such that x squared is equal to a. Here the free variable is a, and you're asking what are conditions on a such that this constraint will become satisfiable, and you get a result that a should be either 0 or a should be bigger or equal to 0. Yeah? Or you can make the solver discover things that you know from high school. You can give it a quadratic equation like the one up there. So you want that this quadratic, this degree 2 equation to have a solution. So you want to have an x such that ax squared plus bx plus c is equal to 0. And then the solver will discover for you that the discriminant has to be non-negative, yeah? Or the equation should be linear or constant. So basically, we will be using the theory of finite fields. And just to recap, so I mentioned two strategies. There was a strategy of using static analysis. This is very scalable, right? But it has many false positives. SMT-based reasoning is much more precise, but it doesn't scale because at the end of the day, you have to solve polynomial equations, which boils down to finding some Gröbner basis or triangulation and so on, which are inherently difficult problems and they do not scale very well. Yeah? So solving polynomial equations are difficult, so we have a tool called PICUS, and Andrea will talk more about it tomorrow at 6. So if you are free, please listen to her talk and come to the workshop at 7 to see it in action. What PICUS does is it just combines this SMT-based reasoning together with some static analysis, so it's kind of an interactive loop between the two, and whenever one gets stuck with the input, it just passes it on to the other, and together they try to solve it. And the nice thing about it is it kind of improves your performance quite a lot, but then it is a difficult problem, so even with PICUS, you run into problems. And for that, we had to kind of see how one can speed up this SMT reasoning, which boils down to deciding to find ways to solve polynomial equations, right? So what could you do? You could either wait for the computer algebra community to come up with new algorithms to solve polynomial equations, but if you take into account that that theory has been going on for decades, it's very unlikely that you will get satisfying results in the near future. I mean, there are great results, but it is just a very difficult problem, right? But another thing you could do is you could exploit the fact that the circuits you are very special. You're not looking at arbitrary polynomial equations, you're looking at polynomial equations that have a very special form. Yeah? So your equations are, depending on your setup, in most cases just quadratic equations, they are very sparse, and so on. Yeah? So then the question is, can I exploit the fact that the equations are simple or have a special form and are simple to kind of speed up things? So you have to kind of understand the system a bit better. So what we did was we attached a graph to the given system of constraints, which keeps track of which of the variables are related directly with each other. Yeah? So basically what we do is we have a graph where each vertex corresponds to a variable, and I connect two vertices if the two variables appear together in an equation. Yeah? So just to show you, this is the graph of the FP multiply circuit, which would have 377 variables and 392 equations. And you already see that you have quite some clusters around, right? Some variables in the cluster on the top left would not directly communicate to the variables down there, so you can try to ease things a bit by exploiting that. Or let me just get rid of the multiple edges, then you see the structure looks a bit different. You have, once you remove multiple edges, you see all of those arms appearing, right? And then you can ask about, okay, the end of one arm over here connects to the center just through one edge, one sequence of edges. What's really going on? What happens in that arm? You try to understand that a bit better. Yeah? And you can use some very nice ideas from graph theory, but basically what you do is, at the end, you understand your graph a bit better. If you look at one of the arms, for instance, I just picked out one of the arms, it just corresponds to these equations and variables, right? And basically what it is saying is that B0, B1 up to Bk, they are bits, because they are all 0 or 1, and x is just given by a binary expression in the form above. Yeah, which would basically just be saying that x is between 0 and 2 to the k plus 1. This is basically just a range constraint, right? Expressed in terms of polynomials. But now the problem is, once you want to get rid of that range constraint and once you feed it into a SMT solver, which will try to use some Gröbner basis, what it will do, it will convert the simple range constraint into a big polynomial equation. Yeah? And the polynomial equation basically will just say that x is either 0, or it's 1, or it's 2, and so on, up to, or it is 16,383. And this is a polynomial of degree 16,384 with coefficients of sizes over 60,000. Yeah? So that's why the SMT solver has problems, because converting into algebra makes things difficult because that's not the right way to deal with such a simple inequality over there. So what we do is, you can't say I just forget about these because these range constraints do appear a lot in circuits, right? So whenever you have range constraints or you have inequalities, you are bound to have bit sums. So that's the main bottleneck. But what you can do is you can exploit the graph structure. You can simplify the arms, treat them as range constraints rather than feeding them directly into the SMT solver. And you can use a separate range analysis on them. And you can combine this with this hybrid method that I had mentioned before of using static analysis. And like that, you can push the number of cases that you can resolve by quite a lot. Yeah? Okay, so I hope I could give you just an idea how wonderful SMT solvers are. I mean, you should go home and start experimenting on an SMT solver. And if that's not enough, go to one of our tools and experiment with that. Thank you very much for your attention. And